Okay, so this one says a 200 milliliter sample of 0.1 molar HCl and a 200 milliliter sample of 0.1 molar HCN are each titrated with 0.5 molar potassium hydroxide, KOH. And it says to find the following for both samples. A, the volume of added KOH at the equivalence point. B, the pH at the equivalence point. And C, the pH upon adding 30 milliliters of potassium hydroxide. So really, we have like a 6-part problem here because we have 2 different samples, one with HCl and one with HCN, and each of those samples, we're trying to calculate 3 things. So it's really like a 6-part problem that we're doing here. So let me go over to the whiteboard so we can get started on this one. And go to the whiteboard here. Okay. It's like, I came prepared today. I already pasted the, the problem into it. Okay, so let's say we start with our, we're looking for A, right? The volume of added potassium hydroxide required to reach the equivalence point. Now, it's important to remember what this term is, equivalence point. What does that, whoops, didn't mean to do that. I was trying to highlight it. There it is. So what does equivalence point mean exactly? Would anybody in the chat like to chime in here on this one? What is the equivalence point? We defined it 2 live streams ago, but I want to make sure we know that. Okay. Not sure how long I should wait, how long the delay is, but I don't see anything in the chat. Okay, so the equivalence point is the point at which the number of moles of acid is equal to the number of moles of base, right? And it's the same regardless of whether you have a strong or a weak acid, right? So moles is just moles. You can have X moles of strong acid. You could also have X moles of weak acid, right? So now it's important to look at these 2 samples, right? So there's 200 milliliters in one, 200 milliliters in the other. So they have the same volume, right? They also have the same concentration, 0.1 molar. But what they have, what don't they have in common, right? Well, they have different chemical formulas, right? One's HCl, one is HCN, right? Now, HCl, that is a strong acid. So if you've been studying chemistry long, or if you've been studying acids and bases for long enough, you probably can just take a look at that formula HCl and just conclude that it's a strong acid because it's been used over and over and over again. It's a very, very common strong acid, right? So HCl, that's a strong acid, and HCN, right, that's hydrocyanic acid, that is a weak acid, right? So that's the main difference, is that one of them is strong, one of them is weak, but how does that affect the volume of added potassium hydroxide to reach equivalence point? Well, in order to do this, we're going to have to convert the concentrations and the volumes that we have of our acids. We're going to have to convert those into moles, right? Now, luckily, that's going to be easy because if we've done one, we've kind of done the other, right? Because they're both the same concentration and the same volume. So let's just start with our HCl, for instance. So let's just say we have 200 milliliters of HCl, right? That's just given by the problem. Now, our concentration is given in molarity, which is moles per liter. And so in order to have a unit that is compatible with our molarity, we need to convert this 200 milliliters into liters, right? So we'll put milliliters on the bottom. We'll put liters on top. Of course, for every 1 liter, there are 1,000 milliliters, right? So now that we have it in liters, we can use the molarity to convert to the amount in moles, right? So it's 0.1 molar. That means it's 0.1 moles for every 1 liter, right? Make sure our units cancel. Milliliters cancels with milliliters. Liters cancels with liters. And we are left with moles, which is what we want, right? We're trying to convert to moles, right? So I'm going to put this calculation in my calculator. By the way, I haven't done any of these problems ahead of time. I just kind of came up with them like loosely based off of my textbook, but I just kind of came up with them, but I haven't actually solved them. So we're doing this live together. All right, so 200 divided by 1,000 times 0.1. I got a value of 0.02 moles of HCl, right? 0.02 moles of HCl. 200 milliliters, converted that into liters, and then used the molarity, 0.1 molar, to convert that into moles, right? Now, when we talk about the term equivalence point, what we're talking about is when, again, the moles of base are equal to the moles of acid. So if we have a 0.02 mole sample of HCl, then that means we're going to need a 0.02 moles of sodium or potassium hydroxide, KOH, right? Because again, that's what equivalence point means, right? Number of moles of acids equal to the moles of base, right? So that is what we kind of start with in this new calculation here. So we need to take this value in moles and we need to convert it into a volume, and we can use molarity to do that, right? What's the molarity of the potassium hydroxide solution? 0.5 according to the problem, right? So I'll put my 0.5 moles down here, and I'll put my 1 liter up there. And just to keep it consistent with the rest of the problem, let's convert this volume in liters into milliliters, right? So we know that 1 liter is equal to 1,000 milliliters, right? Just make sure our units cancel. Moles cancels with moles. Liters also cancel. So we get 0.02. 5. That is 40. I don't know why that's in red, but 40. Oh, it's because I was using that to cancel. 40 milliliters of potassium hydroxide, right? 40 milliliters of potassium hydroxide. So we just figured out the volume of base that needs to be added in order to reach the equivalence point in this strong acid, strong base titration, where you have HCl being titrated with potassium hydroxide, right? Okay, so what would happen if we now switch this over to HCN? So instead of having 200 milliliters of our 0.1 molar HCl, we have 200 milliliters of 0.1 molar HCN. Well, all I really have to do is just take Cl and just kind of replace it with N, right? HCN, right? And it's basically the same thing, right? I'll just put an N like that, right? So it doesn't matter whether this acid is strong or weak. The number of moles of it is what it is. It's the number of moles of it, right? So we get the same exact value in moles for the HCN, right? Because the initial volume and concentration of the two samples were the same. And then that's how much of your base you need. So you convert your way to the volume required to reach equivalence point, which is 40 milliliters. So whether the acid is strong or weak doesn't make a difference on the volume that's required to reach equivalence point, right? Because again, equivalence point is simply the number of moles of acid is equal to the number of moles of base, right? Okay, so that pretty much takes care of A for both of them, right? 40 mils for both of them. So let's go ahead and actually, I'll just erase all of this. We'll just start over. Fresh, clean slate. So we have B, right? Let's move on to B. It says the pH at the equivalence point. Now, again, we're going to calculate this for two different samples, one for the HCl sample and one for the HCN sample. Let's start with the HCl, right? So let's imagine. So let's look at this, right? So we have, if we write out the neutralization reaction, right? So you have some OH minus, that's the hydroxide, right? That's the important part of potassium hydroxide. So that represents what you add, right? That represents the stuff in the burette that's falling downward into the analyte, and then the analyte, that's H+, right? And that's the important part of HCl, right? And of course, they react to form water, right? Now, initially, how many moles of H+ did we have? Well, I think we calculated it at 0.02, right? We just did this calculation earlier, starting with volume and then converting it to liters and then using molarity. Yeah, so 0.02 moles, right? And so again, if you're at equivalence point, that means that the number of moles of each of these are the same, right? So it's 0.02 moles, right? And so at this point, you basically have these things canceling each other out. They neutralize one another, right? Because the amount in moles of hydroxide that you threw in is exactly the same as the amount of hydronium, or H+, that you had in the beginning, right? And so there's no source of H+, or OH- for that matter, other than in the what's called the auto-ionization of water. So this is something that I brought up several times before. Auto-ionization of water. It's basically water reacting with water to form hydronium ion and hydroxide ion, right? And the equilibrium constant associated with that process is called the ion product constant for water, and it's abbreviated Kw, right? And Kw is equal to 1.0 times 10 to the minus 14, and that's at 25 degrees Celsius. So all these problems, we can just assume that they're at 25 degrees Celsius, because that's kind of how like the textbooks are written. Because I don't know, it would take a lot of pages to do these at different temperatures, right? So we kind of just normalize it 25 C, right? And so 1.0 times 10 to the minus 14. I think it would help to write the equation for that that process, right? So auto-ionization of water is when you have a water molecule reacting with another water molecule in an equilibrium sort of fashion to produce hydronium H3O plus and hydroxide OH minus, right? And so we have this 1.0 times 10 to the minus 14. That's just the equilibrium constant associated with this reaction, right? And so really, like the water, you can exclude that from the equilibrium constant expression because it's a pure liquid. Pure solids and liquids do not appear in equilibrium constant expressions. And so what we really have here is, I'll just sort of write it in over here. We have concentration of H3O plus times concentration of OH minus is equal to 1.0 times 10 to the minus 14. Now, if the solution is neutral, then that means the amount in moles of H3O plus must be the same as the amount in moles of OH minus, right? And so really, each one of these things is simply the square root of this number right here, right? 1.0 times 10 to the minus 14, right? So if I calculate, let's see, if I want an expression for H3O plus, right? Because again, H3O plus, that's what we need, right? That's the concentration that we need because the negative logarithm of that is pH, and that's what we're being asked to calculate is pH, right? So that means that the H3O plus concentration must be the square root of 1.0 times 10 to the minus 14, and that is 1.0 times 10 to the minus 7, right? 1.0 times 10 to the minus 7. So now that we have the hydronium concentration, we can just simply take the negative logarithm of it to get pH, right? So pH, squeeze it in down here, equal to the negative logarithm of 1.0 times 10 to the minus 7. Negative logarithm of 1.0 times 10 to the minus 7. And that is equal to 7. So we just basically discovered that the pH at the equivalence point of any strong acid, strong base titration is always going to be 7, right? Because you have the same number of moles of hydroxide as you do hydronium. They neutralize one another. So the only source of hydronium is the auto-ionization of water, which is given by the equilibrium constant 1.0 times 10 to the minus 14. Take the square root of that. That gives you the hydronium concentration. Take the negative log of that, and that gets you the pH. So I know that was like a really long-winded way of telling you about how the pH of a strong acid, strong base titration is always 7. But that's because I kind of want you to understand it. Because if I were to just tell you, yeah, the pH of a strong acid at equivalence point of a strong acid, strong base titration is always 7. Like you might memorize that, but you wouldn't really understand why that's the case. So, all right. So now that we're done with that, so we know the pH at equivalence point in the case of the HCl is going to be 7, right? So let's do the pH at the equivalence point in the case of HCN, hydrocyanic acid. Okay. So we need to figure out how many moles of HCN we have initially that are being titrated with our hydroxide ions here, right? And I think we calculated it earlier. It was 0.02. 0.02. Do you think I should calculate? Does anybody in the chat think that I should calculate this one? Just given, you're given concentration of HCN and volume of HCN, and can you convert your way to moles, or do we know how to do that step? Should I walk through it? Yeah, I think so. I'm going to walk through it. Okay. So, I mean, repetition is the key to success, right? So there's no harm in doing it again. Okay. So if we have a 200 milliliters of HCN, right, we're trying to convert that to moles. Well, we need to convert it into liters first, because that's what's compatible with the molarity, right, moles per liter. So we have milliliters down here, we have liters up there. There are 1,000 milliliters in 1 liter, right? And now that we have our volume in liters, we can use molarity, right? Liters on the bottom, moles on top. Since we have a 0.1 molar solution, it's going to be 0.1 moles per liter for 1 liter. Always make sure those units cancel. That's how you catch yourself if you made a mistake. So we have 200 divided by 1,000 times 0.1. And I'm not good enough at mental math to calculate this. I'll just admit it. I'll use my calculator. But I'm pretty sure it's 0.02. If anybody would like to double check me on that, yeah, let me know. I think it's 0.02, and that's moles of HCN, right? 0.02 moles of HCN. Okay. So now that we have that, I think we can delete all this calculation stuff that is leading up to getting that 0.02 moles of HCN. And now we can set up a sort of a table, right? Not an ice table, but a table that's kind of similar to an ice table that helps us sort of track the progress of the titration, right? Let's see. So let's write that neutralization equation here. I'll just do it in blue, right? So we have the OH minus ion, that's the hydroxide ion. That's what we're adding, right? And then we have the HCN that is already existing in that solution, right? And that's going to react to form the cyanide ion, that's Cn minus, right? And some water, right? And so now what we can do is we can sort of track the progress of the reaction. So I'm going to create 3 rows in this table, right? There's going to be the conditions before the addition. Trying to write before. It's not really good. I'm kind of running off the page a little bit. Let's see if I can take this whole thing. Try to grab this whole thing so far and move it just a little bit. Yeah. Okay. So we have the conditions before the reaction begins. We have what the addition is. Addition. And then we have the conditions after the addition is complete. After. Okay. So let's start populating the cells of this table, right? So we know that initially we have 0.02 moles of HCN. So I'll go ahead and populate that, 0.02 moles, right? And we can assume that we have approximately 0 moles of hydroxide ion. Technically, we do have some hydroxide in there before the addition, but the amount of hydroxide that we have before the addition is so small compared to the amount of hydroxide that we're about to add during the addition that you can disregard it. It's really, really small. And then finally, for the cyanide ion, Cn minus, the conjugate base of HCN, what do we have? We have 0, right? There's not any of it yet. Okay, so what is the addition, right? Well, we're adding, hang on, it says the equivalence point, right? Yeah, so the equivalence point means that the amount in moles of the added base is equal to the amount in moles of our original acid, right? And so the addition here is going to be 0.02 moles of hydroxide, right? So what is that going to have? What effect is that going to have on this titration? Well, after the addition, right, the hydroxide has basically converted all of the HCN into CN minus, right? The HCN was able to neutralize all of that added OH minus, but at the cost of being completely depleted by this reaction, right? Because the amounts of them are the same. So afterwards, we have approximately 0 moles of OH minus. We also have 0 moles of HCN, right? Because it's all been neutralized, it's all been consumed. So it's been converted into the cyanide ion, 0.02 moles, right? So basically what's happening here is that because these are being, because this is a neutralization reaction, right? The amount in moles of your acid is going to decrease by a certain amount, right? It depends on how much base we add. And the conjugate base of your acid is going to increase by that same amount. So that's what happened here. So basically, what we have here is a situation in which we have 0.02 moles of cyanide ion acting as a base and nothing else, right? So we need to figure out we need to work out like an equilibrium problem, right? We have a weak base, right? And we need to do that ice table thing where we have initial concentration. By the way, what is the initial concentration, right? I mean, so we have the amount in moles, but we don't have the concentration, right? In order to get concentration of CN minus, I'm drawing this up here where I am, I just realized. Let me put that down here, right? I'll do it in like purple or something. So in order to get concentration of CN minus, we need to take the amount in moles that we have, 0.02 moles, and we need to divide it by the volume. And when I say volume, I'm talking about the total volume, right? The volume required to reach equivalence was 40 milliliters, right? Plus the additional 200 milliliters that we started with, right? And so what is that going to be, right? So we have 0.02 moles of cyanide, right? And we need to divide that by the total volume, which we just said was 240 milliliters. Again, that's the 200 milliliters that we started with, plus the 40 milliliters of potassium hydroxide required to reach the equivalence point, right? So 0.02 over 240 milliliters, which is 0.240 liters, right? So that becomes our concentration. So allow me to put this into my calculator real quick, and I would encourage anybody who is watching to follow along with your scientific calculator. I think that'd be the best way to get the most out of doing these practice problems, is to do them together. All right, so 0.02 divided by 0.24. Okay, what I got was 0.083. I'll just do it to 2. Oh, I'm off the page here. Let me fix that. I lost one of my concentration brackets. Oh well. Yeah. So it's 0.083 molar, right? And so this titration problem has now turned into like a chemical equilibrium problem involving an anion acting as a base, right? Because again, all of our HCN has been depleted. It's been converted to CN minus, conjugate base, by that added hydroxide. Hopefully that makes sense. If it doesn't, I would hope you would tell me about that. Okay, so let me erase all of this stuff that we no longer need. No longer need a lot of this stuff. We do need the initial concentration of CN minus. That is very, very important. Okay, so let's write the chemical equation for this equilibrium process. So we have CN minus, right, aqueous, and that's going to react with water, H2O, which is liquid, right? So Cn minus is going to accept a proton from the water, and so that's going to give us HCN aqueous. And then the water, having donated a proton, having acted as an acid, is left with just OH minus. That's aqueous, right? Okay, so now we have a chemical equation, right? Now we can sort of write the formula or the expression for the equilibrium constant according to this equation here. Now, I haven't really looked at the Ka for this acid yet. I haven't talked about it yet. We haven't had to talk about it yet, but unfortunately, that luck has run out. We have to know what the Ka value of hydrocyanic acid is, HCN. I actually wrote it down. I'm looking at it right now. So the Ka, I'll just do it right here. The Ka, right, is 6.2 times 10 to the negative n, right? So what is Ka, right? Ka is just the acid dissociation constant, right? Blair says, hello from outer space. Hey, how's it going, man? Anyway, so yeah, this is the acid dissociation constant. So all this is just the equilibrium constant associated with the equilibrium reaction of hydrocyanic acid with water to produce cyanide ion and hydronium ion. So, but we have Ka, but what we really need is Kb, right? What we really need is Kb. So how do you get Kb from Ka? Well, what you do is you understand that Ka times Kb is always going to be equal to Kw. Again, that's the ion product constant for water, right? So the product of Ka and Kb are Kw. So if you have Ka and you want to know Kb, all you need to do is take Kw, and again, Kw, what is that? That's 1.0 times 10 to the minus 14 at 25 degrees Celsius, right? And you divide it by your Ka value, 6.2 times 10 to the minus n, right? So the product of Ka and Kb are Kw, and so all you need to do is take your Ka, divide Kw by it, and that gives you Kb, right? So the Kb is going to be equal to what? Well, I got to perform this calculation in my calculator. And again, I would invite all of you guys to do the same. And by the way, if anybody is feeling generous, you're more than welcome to leave me a tip in the form of super chat, or I actually just got my Streamlabs thing to work, so there should be a link down in the description that says support the stream. And I think it's like streamlabs.com/BensChemVideo, something like that. And that's actually a good way to donate, because it's they take a lesser cut of it than YouTube does with their super chats. All right, and that pitch is over. Divided by 6.2. Okay, what do we got? Oh, that's a small number. I'm gonna have to put this in scientific notation. Kb is what I got. Oops. What I got for Kb is 1.6 times 10 to the minus 5. 1.6 times 10 to the minus 5. That doesn't look good. My power is like bigger than my 10 here. Minus 5. Okay. 1.6 times 10 to the minus 5. That's Kb. So I'm going to erase some of this stuff and sort of leave my Kb, which is what I really want. Delete all that. Just drag my Kb over here. Okay, so now we can take another look at this equation, right? And now we can write the equilibrium, the expression for the equilibrium constant, right? It's always just the concentration of products divided by the concentration of reactants. So in this case, that would be HCN, right? Concentration of, HCN times the concentration of OH minus, those are the products of this equilibrium reaction, divided by concentration of CN minus. And we can leave the water alone because, again, water does not appear in equilibrium constant expressions. It's pure liquid. Its concentration does not change over the course of the reaction. Demeen says, may I ask, because I missed it, why did you convert Ka to Kb, right? Well, that's a good question. We needed to convert to Kb because Kb is what describes the equilibrium that's going on, right? Kb is what describes this equation right here, in which these two, HCN and OH minus, are the products, and CN minus and water are the reactants. Why? Because, again, all of our weak acid has been converted into weak base, right? We no longer have any HCN anymore. Now we have a 0.083 molar solution of CN minus, right? And so CN minus, that's going to act as a base. It's going to take a proton from water, and it's going to do this in an equilibrium sort of way, right? So I hope that answers your question. All right, so we know that Kb is equal to the concentrations of the products divided by concentration of the reactants. At this point, we can use our ICE table, so I'll sort of fit that in here. Again, I stands for initial, C stands for change, E stands for equilibrium, right? So initially, what do we have? 0.083 molar in the case of CN minus, right? We can assume that we have 0 of each product. The change, well, the change of this, it's going to decrease by an amount that we'll call x, which means HCN and OH minus are going to increase by that same amount, x, right? And so now at equilibrium, it's just initial and change, right? So it's 0.083 minus x, and then these two are just x and x, right? So that's our ICE table, right? So we know that, let's see if I can sort of move this around a little bit. I think I'm a little cluttered here, so I'm going to try to move some stuff. Of how well it's going to go. Got a lot of stuff up here. Got most of it. Yeah. Equilibrium problems are difficult. They just take up so much space. Anyway. All right, so where did that 0 come from? Oh, I think it came from that. Okay, so all right, so we know the expression for the equilibrium constant, right? So we can now substitute everything that applies in terms of x, right? So concentration of HCN, well, that's just x. Concentration of OH minus at equilibrium, that's just also going to be x. And then that's x times x, so we can just rewrite that as x squared, right? That's kind of a way to simplify that one. And then with CN minus, well, we know that that is 0.083 minus x, right? So we have this sort of quadratic equation here. 1.6 times 10 to the minus 5 is equal to x squared over 0.083 minus x. Now, quadratic equations are pretty tricky to solve. You have to use the quadratic formula, which I don't really like to do that. I'm not a big fan of the quadratic formula. So what I do is I just use the x is small approximation. Whoops, am I still on the page? Sorry. What I do is I just use the x is small approximation. So I just get rid of that x, just cross it out, just ignore it, right? And what I'm saying here is that I think x is really, 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 really small compared to the number from which I am subtracting it, in this case, 0.083, right? And so that simplifies our equation dramatically, right? X squared over 0.083 is equal to 1.6 times 10 to the minus 5, right? And so if we could just continue algebraically and solving for x, right? And by the way, x is just, OH minus concentration at equilibrium. That's what's going to help us eventually calculate our way all the way to pH, right? So 1.6 times 10 to the minus 5 equals x squared over 0.083. And so we get, let's see if I can write it down here, x squared is equal to product of 1.6 times 10 to the minus 5 and 0.083. So to get from here to there, all I've done is just multiply both sides of the equation by 0.083. And then to get x, I'm just going to do it the short way. So to get x, I'm just going to take the square root of this entire expression here, right? So x, which is equal to concentration of OH minus hydroxide, right? That's equal to this thing, the square root of the product of 1.6 times 10 to the minus 5 and 0.083. That was quite a mouthful. Oh, man. All right, so let me calculate that in my calculator real quick. By the way, if anybody would love to have your guys' participation if you guys want. So, all right. That's not square root. Minus 0.083. I think I got it. Double checking my calculation. So what we end up getting here is the hydroxide concentration. Again, that's what x is equal to. Is the number that I got was, I don't know if anybody wants to chime in with their answer. I got 1.2 times 10 to the minus 3. 1.2 times 10 to the minus 3. That's my hydroxide concentration. And you might be thinking, well, that's great that we have hydroxide concentration, but how do we get pH from that? Good question, person I just made up in my head. The way that we get pH from that is, there's a couple ways to do it. The way I do it, the way I like to do it is to calculate the pOH first. So the pOH, right? That's just the negative log of concentration of OH minus, right? So concentration of OH minus is this thing right here. So all I have to do is just take the negative log of 1.2 times 10 to the minus 3, right? We get a value of, I don't know, because I can't do that math in my head. Let's see. Negative log 1.2 10 to the negative 3. I got 2.92. pH is equal to 2.92. I'll just erase all that. Gonna drag that bad boy and throw him over here. All right. So it's also an important thing to remember that the sum of pOH and pH is equal to 14. And that's assuming that you're at 25 degrees Celsius, which is, again, the most commonly reported temperature that you'll see in these kind of problems. pOH plus pH is equal to 14, right? So all that means is that to get pH, all I have to do is subtract my pOH from 14, right? So that means that pH equal to 14 minus 2.92, the pOH. And we end up getting a pH of take it off of scientific notation, 11.0. 11.08. Hopefully you guys got the same thing. Oh, I see Demeen has gotten the same answer that I did, so that's good. I'm glad we got the same answer, because if we got different answers, then one of us would be wrong, and I sure hope that wouldn't be me. So, yeah, that was a pretty involved calculation, wasn't it? Like, that took forever, didn't it? Oh my goodness, right? So it started with that stoichiometry calculation for the titration, right? Understanding that all of the HCN got converted into CN minus, right? And then, you know, we had to get the Kb of Cn minus by understanding that Ka times Kb is equal to Kw. And we had to do our ice table, solve our quadratic equation, calculate POH, and then use the relationship between POH and pH to finally get pH. So yeah, these calculations are, I wouldn't call them like difficult. It's not like we're doing like crazy, like, you know, differential equations, you know, crazy type of math or anything like that. But they are very lengthy. They do take a long time. And so that's why I always say, like, you know, write out your units, cancel your units, you know, try not to rush. Because, you know, as not so hard as the problems are, I mean, it's easy to make a mistake when it's that long. You're going for that long. So, okay, so we figured out the pH at equivalence point for both of these samples of acid, right? So I'm a much bigger fan of the strong acid, strong base titration than I am the weak acid, strong base. So much easier because, you know, pH is always 7, at least at equivalence point. All right, so last one says pH upon adding 30 milliliters of potassium hydroxide. 30 milliliters of potassium hydroxide. Well, as you probably know, we're going to have to take that 30 milliliters of KOH, and we're going to have to convert it into moles, right? So how many moles is that? Well, let's convert our volume to liters. So we have 1,000 milliliters at the bottom, 1 liter on the top. Then we can use the molarity of that KOH to go from liters to moles, right? So we have 0.5 molar, so we have 0.5 moles of KOH for every 1 liter of KOH. I'm going to go ahead and cancel my units. Cancel. Okay, that looks good. So 30 divided by 1,000 times 0.5. Who's got it? Anybody? I got a value of 0.015, and that's moles of KH, right? 0.015 moles of KOH. So I'm going to go ahead and just erase all this stuff that we'll just sort of keep that in mind, right? So we also need to know how many moles of acid that we start out with, which we've done this calculation a couple of times throughout this presentation, but I think we can do it again. So if we start with our HCl sample, right? So we have 0.1 molar, right? So start out with 200 milliliters. 200 milliliters of your acid, right? We can convert that to liters, right? 1,000 milliliters, 1 liter. And then the molarity, of course, that's 0.1 moles per 1 liter. Cancel, right? And we end up with 0.02, I think is, pretty sure. If I'm wrong about that, then I've gotten a lot wrong so far in this presentation, but yeah, 0.02 moles of HCl, right? I'm just double checking just to make sure, so I don't look like an idiot on the live stream. Yep, 0.02, that's right. Okay, so those two values are what's going to help us do this problem here, right? So, all right, let me drag this here. I'll drag you there. So again, with these titrations, I really like to just start by writing the equation for the neutralization reaction, right? So what does that look like, right? So we have OH minus, that's what we're adding, right? And that's going to be added to H plus, right? Because that's what this HCl produces in aqueous solution. It produces H plus or H3O plus. I mean, however you want to think about it, right? And that's going to react to produce water, right? And so we can track the progress of the reaction before. Again, I'm off the page here. Sorry, guys. before, and then what the addition is, and then after. Before, addition, after the addition, right? So in the beginning, we have approximately 0 moles of hydroxide, and we have 0.02 moles of H+, right? Coming from our 0.02 moles of HCl, right? For the addition, what are we adding? Well, we're adding 0.015 moles of hydroxide ion, right? And so what happens after the addition? Well, the H+ is going to neutralize all of the hydroxide ion, right? Because there's more of it, right? It's a battle of, you know, who's got more moles, hydroxide or H+, right? And so this 0.015 moles of hydroxide is going to take 0.015 moles of H+ with it to make water. And there's still going to be some H+ left behind, right? So it's 0.02 minus 0.015, right? And so after the addition, when all that's done, you're going to have 0.005 moles of H+, right? 0.005 moles of H+. So you have moles of H+, right? So we need concentration of H+ in order to get pH calculation, right? So erase this over here. So what is the concentration of H+, right? What is that? That's going to be the amount in moles that we just calculated, 0.005 moles of it, divided by the total volume. What's the total volume? Well, we started out with 200 milliliters in our HCl sample, and we added 30 milliliters of potassium hydroxide to it. So it sounds to me like the total volume is going to be 230 milliliters, right? Which is 0.230 liters. I did that little conversion to liters in my head just there. I hope you don't mind. Okay, so what's the concentration of H+? Well, 0.005 divided by 0.230. I got a value of 0.022, 0.022. And then finally, to get pH, we need to take the negative logarithm of that value, of that 0.022 molarity, right? Okay, so what is that value? I got a value of 1.66. 1.66. That is what I got. And I hope that's right, because, again, I'm doing this for the first time, just like all you guys. But, I mean, it seems logical, you know? A pretty logical approach to get that answer. So, unless I did had a calculator error or something like that, I think that's correct. Okay. So, now we figured out the pH upon adding 30 milliliters of our potassium hydroxide. We want to do the same for the HCN, the weak acid sample, right? So I'm just going to take everything and delete it. Yeah, looks like Demeen got the same thing. Very cool, very cool. We're both on a roll tonight. Okay, so again, we're getting the pH upon adding 30 milliliters of KOH, and we're going to do that for the case of our HCN, right? So in the very beginning, we need moles of KOH, moles of HCN, right? So we just calculated those for the strong acid example, and the values are going to be the same. It's just the formula is HCN instead of HCl, if that makes sense. So in other words, when we calculated 0.02 moles of HCl, well, that's the same thing is going to apply to the HCN, right? Because there are two samples that have the same volume and the same concentrations. So of course, they'll have the same amounts in moles, right? So I'm going to skip that calculation and get to the good titration stuff, right? And then also, we did the same thing a moment ago with our HCl, right? We calculated the moles of KOH to be 0.015 moles of KOH, right? So again, I want to save you guys the pain of having to do those conversions all over again when we've already done them before. If that is not something you're into, if you want me to see me like convert it out every single time, then let me know. I don't know. I like to skip things when I can, but I also want to make sure that everybody understands. So I don't know. All right, so Demeen says, so for this step, we convert Ka to Kb and do the same calculation because we end up having an excess of the strong base. I don't know which example you're talking about. If you're talking about strong acid, strong base titration, there's no Ka or Kb, right? Ka and Kb are for weak acids, right? So you're not going to be using any kind of Ka or Kb or anything like that when it comes to strong acid-base titrations. You're just going to look at the number of moles of H+, look at the number of moles of OH-, which one is in excess, right? They're going to react completely, and then one of them is going to be left over, and then you'll calculate pH or pOH based on that. So I think, I hope I explained that well. All right, so because we're going to move on. Okay, so again, we have converted to moles, right? Or we just remember our conversion from last time, right? 0.02 moles of HCN, 0.015 moles of KOH. Now let's write the equation for the neutralization, right? So we're adding OH-, right? And we have HCN initially in the sample, right? And that's going to react, right? This is going to grab a proton from HCN to make water, and CN- is going to, or HCN is going to lose a proton to become CN-, right? So this is basically just describing what happens, right? OH converts a stoichiometric amount of the weak acid to the conjugate base of that weak acid, right? Do I need to repeat that? Let me repeat it. The OH- is going to convert a stoichiometric amount of HCN to CN-, the conjugate base of HCN, right? And so now that we have this table or this equation up, now we can do our little table here where we have before, before the addition, what the addition is, and then after the addition, right? Or what the addition is, and then after the addition. So initially, approximately 0 hydroxide, 0.02 moles of HCN, and no CN-, right? What is the addition? Well, the addition is 0.015 moles, right? And so what is that going to do? That's going to convert 0.015 moles of HCN into CN-. So afterwards, we'll have 0.015 moles of CN-, and we're going to have 0.02 minus 0.015 moles of HCN, right? So 0.005 moles of HCN, right? And so here we have a weak acid and its conjugate base, and we have significant amounts of both of them in this aqueous solution. Let me repeat that. We have an aqueous solution in which there is a significant amount of both a weak acid and its conjugate base. There's a name for that kind of solution. What is that called? It's called a buffer, okay? It's called a buffer, and there's a certain equation that helps us very easily calculate the pH of buffer solutions, and it's called the Henderson-Hasselbalch equation. You may be familiar with it. I hope you are. I've talked about it many times on this live stream series. Henderson-Hasselbalch equation, right? So what does that look like? Well, whoops. Trying to erase, not draw this in red. Henderson-Hasselbalch equation. So that is pH is equal to the pKa plus the log of concentration of base I'll just label it with a B. Over concentration of acid, I'll just label it with an A, right? pH equals pKa plus the log of the ratio of the concentration of the base to the concentration of the acid, right? I got a message from Stanley Chung, says, hi. Hello, Stanley. Good to meet you. I don't think I've ever seen you in my stream before, so welcome. I hope you're doing well. Right now, we're just banging out some acid-base titration calculations, and it's good to have you with us, so thank you. All right, so this is the Henderson-Hasselbalch equation, right? So what is the pKa? I don't think we've seen that so far. Like, what's the pK? We've seen Ka, but we haven't seen pKa, right? So let me go ahead and put the Ka back up on the board here. So the Ka for hydrocyanic acid is 6.2 times 10 to the minus 10. Very, very small number. Very, very weak acid. So how do you get pKa from Ka? Well, pretty easy. P anything is just negative logarithm of that thing, right? So pKa is negative log of Ka, right? So pKa is equal to negative log of this 6.2 times 10 to the minus 10. Negative log of 6.2 times 10 to the minus 10. Let me punch that into my calculator real quick. pKa is 9.2. Yes, 9.2. I'll carry that to one more decimal place. 9.21, right? The pKa is 9.21. And so up here in our Henderson-Hasselbalch equation, right? So that's going to be equal to pKa, that's 9.21, plus the logarithm of concentration of base over concentration of acid, right? Now, since the acid and the base are both in the same solution, by definition, they have the same volume. And so a ratio of their amounts in moles is equivalent to a ratio of their concentrations, right? Because the volumes are the same. So we can simply put the molar amounts of these things here. So we have base, the Cn minus, that's 0.015. And then we have the acid, that's HCN, that's 0.005. Right? And what do we end up getting for our pH? 9.21 plus log of 0.015 over 0.005. Let me calculate that. Hopefully you guys can follow along with me too. That would be super. All right. 1.21 plus the log 0.015 over 0.05. What do we got? I got 9.69. 9.69. That is our pH. Upon adding 30 milliliters of 0.5 molar potassium hydroxide to our 200 milliliter sample of 0.1 molar hydrocyanic acid. Boy, that sure was a mouthful. Gavin Hull says, just subscribed here. Love your videos. I've learned so much. Hey, that's great, man. I'm glad you've been able to find some value in what I do. It just warms the heart knowing that that's the case. So thank you for sharing that. All right. I'm trying to be like the Bob Ross of chemistry videos here. Like, thank you. God bless, my friend. All right. So, I think that's it for that problem. We went through the entire thing. It was very, very thorough. I'm trying to explain things as well as I can and as thoroughly as I can, and hopefully people don't tune out as much. All right, so what I'm going to do here is I'm going to take the next problem and I'm going to paste it into, actually, this one, I think I'm just going to go to the PowerPoint, if you guys will give me a second here. So where are you? Okay, so this one is supposed to be like interactive. Like I would really like for you guys to participate and chime in with your answer when it comes to this problem or this question. So this question says One of these titration curves represents a strong acid with a strong base. The other titration curve represents titration of a weak acid with a strong base. Which one is which? So what do you think? What do you guys think? Which one of these two curves, the one on the left or the one on the right, is the strong acid, strong base titration, and which one is the weak acid, strong base titration? Not a rhetorical question. Really, really want an answer. What I really want is like a convenient excuse to drink some water. All right. Nobody? Demeen says right is strong acid, strong base titration. Does anybody agree with him? Or do you disagree, and why? Okay, so Demeen Harris chimed in with his answer in the chat. Anybody else want to chime in? Whether you agree with him or not? Okay, apparently nobody wants to chime in with their answer to this question. Demeen, you are correct. Yeah, the one on the right is the strong acid, strong base titration curve. The one on the left is the weak acid, strong base titration curve. And there's a couple of things that can sort of help you understand or help you to draw that conclusion. Number one, the equivalence point, the pH at the equivalence point at this one is 7, which is always true for a strong acid, strong base titration. So that's like a dead giveaway right there. Also, you can see that the pH at the equivalence point for this one is actually much higher than 7. It's actually higher than 8. And so that sort of tips you off that you're dealing with a weak acid. And finally, if you look at the initial pH before anything is added, right? For the case of this one, it's like 0, really, really low. That's really acidic, right? And this one over here is like closer to 2. So this is like more characteristic of a weak acid. And having it down here at 0 is more characteristic of a strong acid. And so for anybody wondering how you would draw the conclusion which curve is which in this question, that would be how you would do it. Okay, so I've got another pretty lengthy problem for you guys, if you guys want to see it. We've already been over an hour here, but I can do another one if you guys want, or we can do it another time. I don't know. What do you guys think? Should we do another one? I'm not sure if I could finish it. It's a big one. It's gonna take me forever. I don't know. Demeen says, please, I got an exam tomorrow. Oh, man. You putting that kind of pressure on me, dude? All right. Let me go back to the whiteboard. Okay. I'm going to delete everything here and paste the problem in here. Okay. This is going to take a while. All right. No more complaining. I just got all my complaining out of my system. So we have... how do I get rid of that? Okay. So it says we have a 25.0 milliliter sample of 0.21 molar pyridine, and it's titrated with 0.10 molar HCl. So now our analyte is a base, and we're titrating it with an acid. That differs from all the problems that we've done so far, but as we will see, the same principle applies. And it says find the pH at the following volumes of added acid: 0 milliliters, 10 milliliters, 20 milliliters, equivalence point, half equivalence point, 40 milliliters, and 50 milliliters. So this is a multi-part problem. There's a lot of parts to this. And like I said, I'm not sure if I can finish it because I got to go to bed at some point myself. Busy day tomorrow. Okay, so let's talk about pyridine, right? So what is pyridine? Well, pyridine is actually a chemical or a compound with the formula C5H5N. Right, so pyridine is C5, whoops, didn't mean to do that with the highlighter there. C5H5N, right? And structurally, basically, it's like a 6-membered ring of atoms, and one of them is a nitrogen atom, and the rest are carbon atoms. And so you might see it sort of drawn like this, where you have this 6-membered ring. There's a nitrogen here, right? And then see it sort of written like that. These alternating double bonds here. And at every one of these corners is an understood carbon atom. This is called a condensed structural formula, and you'll learn all about that when you move on to organic chemistry. But that's what pyridine is, right? And pyridine is a base, right? It's a weak base. So if you look it up in your textbook, you can actually find the Kb value, the base dissociation constant value for pyridine. And I think it's probably worth doing at this time to put that on here. So what is the Kb of pyridine? I'll just write it in up here. So the Kb of, and I'll just call it Py because I don't want to have to write C5H5N like every time I describe the formula for pyridine. So I'm just going to abbreviate it with this Py for pyridine is equal to, what's the Kb? 1.7 times 10 to the minus 9. Where did that come from? It just came from a reference table in my textbook. I didn't know that by heart. I didn't calculate it with any information given. That's just a known constant, right? Okay, so we have the Kb, so that's a good start. So that's going to help us initially, right? So let me sort of highlight the current part of the problem that we're on, and then maybe that'll sort of help us stay focused here. Edward Show says, thanks as always for your work, Ben. Oh, you're very welcome, sir. Thank you for your kind words. I truly appreciate it. By the way, if anybody would like to tip me, I finally got my Streamlabs to work now. I think if you go to streamlabs.com/benschemvideos, there's a link to it in the description. You can actually donate. You can actually make your donation like appear on the in the actual screen, like on the stream. I don't know. I have no experience at all with it, but I think I finally figured out how to hook it up to like PayPal and stuff like that. So if anybody's interested in donating, you're more than welcome to, obviously. All right, so back to the problem. So I'm going to highlight what we're on. So 0 milliliters, we're talking about the initial pH, right? The pH of this solution before any HCl is added to it, right? And so what does that look like? Well, again, it's going to be an equilibrium process because pyridine is a weak base. So let's just write out the equation for that equilibrium, right? So what are we going to have? We're going to have, I'll just call it, again, Py. That's the base. That's going to react with water, H2O, to produce, do my equilibrium arrows. That's going to make, I think I'm just going to call it like PyH+. So PyH+. So this is like the conjugate acid of pyridine. This is what happens to pyridine when it accepts a proton from an acid. So PyH+, and then the hydroxide ion, which is OH-. And again, that's just a water molecule after having donated a proton. So it's very, very important that you are able to sort of do this, right? That you're able to say, okay, this is a weak base. That means I can draw this, or I can write this equation in which it reacts with water, and you understand in the products that you're tracking the transfer of an H+, right? The base accepts a proton, and the acid donates a proton, right? Very, very important to understand that. Okay, so go ahead and do our ICE table. So initial change and equilibrium, right? Initial change equilibrium. And so what is the concentration of pyridine initially? 0.21 molar, so 0.21. And then we're assuming that we have none of either of these. What's the change? Well, we know that as the reaction proceeds, the concentration of pyridine will decrease, and the concentration of the conjugate acid of pyridine and the hydroxide ion are going to increase by the same amount. So we're using the variable x. Minus x for the reactant, plus x for the products, right? Okay, so, and then what does that look like at equilibrium? Well, equilibrium for pyridine is going to be 0.21 minus x. And then for the conjugate acid, that's x. And for hydroxide ion, that's also x, right? And so now we have expressions for the equilibrium concentrations that we can use to sort of build a quadratic equation on our way to solving this problem, right? Okay, so we know, right, that Kb, which is equal to some black. we know that Kb, which is equal to 1.7 times 10 to the minus 9, that's equal to what exactly, right? That's equal to the concentration of the products over the concentration of the reactants, right? This is the law of mass action. It's true for any equilibrium reactions, products over reactants, right? So what are we going to have here? So we have PyH plus, OH minus up here. We have just plain old pyridine down here. And again, we ignore water because water is a pure liquid. Pure solids and pure liquids do not appear in equilibrium constant expression, right? And so at equilibrium, well, we know their values in terms of x, so we can just sort of substitute, right? And so this up here is x, this over here is x, right? So that's x times x, so I'll just rewrite that as x squared, right? Simplify that down. And then the concentration of pyridine, well, that's 0.21 minus x, so 0.21 minus x, right? And then we can employ the x is small approximation, right? We're going to assume that this x here is much smaller than 0.21 and can be ignored from this part of the equation. So I'm just going to strike that out. And then what are we left with? Well, we're left with x squared is equal to, let's see, let me drag this across so I can get some more room here. Just want to some more room here. Okay. Okay, so, all right, so we have x squared is equal to this 1.7 times 10 to the minus 9 times 0.21, right? So that, and again, all I did was just multiply both sides of the equation by this 0.21, right? So we get this expression here, x squared is equal to this product right here. And then to get x, well, all we have to do is just take the square root of this whole thing, right? So we have the square root of the product of 0.21 and 1.7 times 10 to the minus 9. And remember, x in this context is equivalent to the equilibrium concentration of hydroxide ion, OH minus, and that's going to help us move forward to get pH. Okay, so this calculation here, what is that? Pretty long-winded calculation. The calculator that I'm using, you can actually put that whole thing on one line. I love this calculator; it's awesome, and it's old too. They were really built to last back in the good old days. Square root of product of 0.1, 0.7, 10 to the negative 1.7. Negative 9. Did something wrong in my calculator. I'm getting a syntax error. How do I get out of this? Okay, I figured it out. It's a very, very small number. All right, let me check the chat. I've been like looking down at my calculator trying to figure out what the hell's going on with it. So I'm gonna make sure I follow along here. 1.89 times 10 to the minus 5 says Demeen. Yeah, that's correct. I got the same thing. I'm not even bullshitting you, man. 1.89 times 10 to the minus 5, and that of course is molar, right? So we don't need our ice table anymore. I'm going to delete all that stuff. We're good. Actually, you know what? I should. Oh, oh no. Okay, I think I got it. I think I saved what I need. I wanted to leave the KB for pyridine up there. Delete all that. It said 1.89 times 10 to the minus 5. Okay, so now that we have hydroxide concentration, we can calculate POH and then get pH from that, right? So POH going to be the negative log of the hydroxide concentration, 1.89 times 10 to the minus 5. What is the POH? Calculate it real quick. negative log 1.9 10 to the negative 5. Very, very important to be able to use scientific notation on your calculator well and accurately and effectively, so that you're not hung up on your calculator when it's time to do well on the test or whatever. All right, so POH is equal to 4.72. That's negative log of 1.89 times 10 to the minus 5, 4.72. And we also understand, or at least we should, that the sum of pH and POH is equal to 14, right? So to get pH, all we have to do is to take our POH and subtract it from 14, right? So 14 minus 4.72, and that gives us a pH of 9.2. 9.2. So that's the initial pH, right? And again, that's just a standard equilibrium problem, something that, if you've been following along with my live streams, we've done time and time and time again. So at this point, it should be like second nature at this point to bang out problems like this. There's nothing like new, there's nothing titration-y, for lack of a better term, about this one. It's just like a chemical equilibrium problem. Acid base, right? Okay, so now what we're going to do is we're going to move on and talk about 10 milliliters, right? 10 milliliters. So what is the pH on adding 10 milliliters of 0.10 molar hydrochloric acid to a 25 milliliter sample of 0.21 molar pyridine? That is a mouthful. I'm going to have like no voice by the end of this thing, man. Oh, boy. This is what I do for you guys. I love you guys. All right. So first what we need to do is we need to understand how many moles of pyridine that we have initially, and we need to understand how many moles of HCl are added, right? We have volume, we have concentration, so we can convert our way to the moles, right? Starting with pyridine, right? So we have 25.0 milliliters of pyridine. Convert that into liters. Put milliliters on the bottom, put liters on the top. There are 1,000 milliliters in 1 liter. Now we're going to use the molarity. What's the molarity of the pyridine? That's 0.21 molar. That means for every 1 liter, we have 0.21 moles of pyridine. Double check, make sure units cancel out. Looks like they all do. 25 divided by 1,000 times 0.21. And again, I did not solve these ahead of time. I'm doing them here live for the first time along with you guys. So let me calculate this one out real quick. 25 divided by 1,000 times 0.21. Okay, I got a value. Let's see. I'll just do it in decimal form. 0.00525 moles. By the way, if anybody wants to chime in with their thoughts, any feedback that you can provide, I would certainly appreciate. You can even tell me, hey, this sucks. Like, you need to find a better way to teach this shit. I don't know. But I won't know unless I get feedback. So I would really appreciate it. All right. So 0.00525 moles. That's how much pyridine we have. So what I'm going to do is I'm going to just kind of erase all this stuff that led up to that. Just kind of table that. Didn't get all of it. Gonna drag this one off to the side here, much out of the way as I can. And that's I should really put pyridine on there. 525 moles of what? Pyridine. PY. Okay. So now we're going to do the same with our HCl, right? So it says here 10 milliliters, so it's 10 milliliters of HCl. That's how much we're adding, right? We can convert that into liters quite easily. So the liters, 1,000. And we can convert using molarity. So it's 0.10 moles per liter, right? So for 1 liter, we have 0.10 moles of our HCl. And that's going to be, cancel the units out. So we have 10 divided by 1,000 times 0.1. 10 divided by... What I got was 0.001 moles. It's ugly looking M right there of HCl. 0.001 moles of HCl. All right, so just as I did with the pyridine, I'm just going to delete this conversion stuff and sort of drag my HCl off to the side here. Get right over there. There you go. All right. Okay. So now we're getting close here, guys. Now we can sort of do the titration calculation, right? So the first step, very, very important that we can write the equation for the neutralization, right? That we can write the equation that describes adding that HCl or H plus, really, that's the reactive part of it, adding that H plus to that pyridine, right, to produce the conjugate acid of pyridine and water, right? So let's do that. So we have our H plus, what we're adding that to our pyridine, right? And that's going to react, form the conjugate base of pyridine, I'll just call it PyH plus, and water, right? So this equation literally describes what happens when we add the acid to the base, right? It converts a stoichiometric amount of that, of that weak base into its conjugate acid. So we're going to label this with our 3 rows here. So we have before, right, B4, because I don't have much space here. We have the addition. For that either. And then we have after, right? So we're going to track the progress of this reaction. We're going to look at the conditions before and after, and also look at what the addition. Whoops. Clean this up a little bit. All right. So, initially, before the addition, we essentially have 0 H plus. I mean, yes, we do have some H plus in there, but it's very, very small compared to the amount of H plus that we're about to add, right, in this row here. So we can assume that that's approximately 0. Pyridine, well, we just calculated the amount of pyridine in moles. That's 0.00525. So it's 0.00525 moles. Right, and we don't have any conjugate acid of pyridine in the beginning. And then what is the addition? Well, the addition is 0.001 moles of HCl, right? 0.001 moles of HCl, right? And so again, what that acid is going to do is it's going to convert a stoichiometric amount, in this case 0.001 moles of pyridine, to the conjugate acid of pyridine. Hang on. So that means that after the addition, after this is all said and done, we're going to have 0.001 moles of the conjugate acid of pyridine, right? And we're going to have this 0.00525 moles minus 0.001 moles of pyridine, right? That's going to be how much pyridine we have left. So it's 0.00425, right? 0.00525 minus 0.001. 0.0042, right? Yeah. Okay, so now we have the amounts of weak acid, the amounts of weak base, or weak base and conjugate base of the weak acid, right? We have those amounts. So at this point, it looks like we have ourselves a buffer solution, right? Because we have significant amounts of both a weak acid and its conjugate base, or more accurately, a significant amounts of a weak base and its conjugate acid. And so now we can use the Henderson-Hasselbalch equation to solve this problem, right? We can use the Henderson-Hasselbalch equation, which is very, very convenient. It's a very, very convenient way to solve for this. Let's see. So I'll do this purple color here. So, all right. So what is that equation? So we have pH is equal to pKa plus the logarithm of the concentration of base over concentration of acid, right? pKa, pH is pKa plus logarithm of base over acid. Okay, so we have base, we have acid, right? The base in this case, 0.00425, 0.00425. Kind of drew it curling up there, whatever. All right, and then we have the acid, 0.001. And then all we need to do is to put the pKa in there, right? Now, pKa is going to be kind of annoying because we don't have pKa. We don't even have Ka, but we do have Kb, right? So there's a couple of ways to get pKa from Kb. This depends on your preference, really. So I think I'm going to choose, what am I going to do? Yeah, I'll do the Ka, Kw way. Okay, so we know that, I'm just talking to myself here on a live stream. All right, so we know that, I'll just write this in down here, that the product of Ka and Kb equal to Kw. Kw, that's the ion product constant for water, 1.0 times 10 to the minus 14 at 25 degrees Celsius. So we're in a situation here where, well, we know Kb, and of course we know Kw, it's constant. So we can calculate Ka pretty easily, right? It's just going to be, write it in here, it's going to be Kw divided by Kb, right? And again, the only reason why we're calculating Ka is because we're trying to get pKa so that we can use this Henderson-Hasselbalch equation here. I hope that makes sense. All right. So Kw, again, that's, what is that? Yeah, that is 1.0 times 10 to the minus 14 Kb. 1.7 times 10 to the minus 9. I have it sort of jotted down right here. Again, that's just from a reference table. Either the problem will give you that, or you'll have to look it up, but common knowledge, right? Okay, 1.0 times 10 to the minus 14 divided by 1.7 times 10 to the minus 9. You calculate that real quick. And again, I would encourage anybody to follow along and do the same. Very, very small number. Okay, so for Ka, I got 5.9 times 10 to the minus 6. 5.9 times 10 to the minus 6 is the Ka value. And again, the only reason why we're doing this is so that we can get pKa to plug it into the Henderson-Hasselbalch equation, right? And so it looks like I have, I can delete this, all this stuff here. Don't need it anymore. We got what we wanted out of it. Okay. All right, so we have our Ka, and now we have to calculate our pKa, right? Earlier, I said the p of anything is just the negative logarithm of that thing, right? So the pKa is going to be the negative log of Ka. So that's negative log of 5.9 times 10 to the minus 6. Calculate that. Negative log 5.9, 10 to the minus 6. I got 5.23. 5.23. That's pKa, right? Okay. Now we have all the pieces we need to solve this problem, right? We got our amount of base up here. We got our amount of acid down there. We got our pKa now, so let me plug that in. pKa is 5.23. We have 5.23 plus the log of 0.00425 divided by 0.001. Calculate that. Okay. I feel like I should put some music on or something, like just have some music playing in the background so that the silence while I'm looking at my calculator isn't as awkward. I don't know. What do you guys think? Let me know what your thoughts are in the chat. Okay, so I got 5.86. 5.86. 5.23 plus the log of this whole mess here. I got a value of 5.86. That is the pH upon adding 10 milliliters of our 0.10 molar HCl to our 25 milliliter sample of 0.21 molar pyridine. Yeah. Good stuff, right? What do you guys think? Seriously, I want to know what you guys think. Like, are these problems, is doing them helpful? Is talking through them the way that I am helpful? Am I talking too much? Am I not skipping steps when I should be? I don't know. I don't know. I just need feedback. All right. Okay, so now we're going to move on to 20 milliliters. Yeah, there's no way I'm going to have time to do all these tonight. Maybe we should just do, I don't know. Let's just do equivalence point and 1/2 equivalence point. What do you guys think? You know, before I had kids and everything, like I could probably just stay up all night doing these kind of things and just have like a, you know, like a 12-hour stream challenge doing chemistry problems the whole time. But, you know, the dad duties are calling. So there's a limit to how much time I can spend, even though I'd love to be with you guys all night. All right. So we're going to do equivalence point. Okay. So we're going to calculate the pH at the equivalence point. Now remember, equivalence point, all that means is that the number of moles of acid that we're adding is equal to the number of moles of base that we have originally in our sample, right? So now I'm an idiot and I deleted the calculation of moles of pyridine earlier, but I guess I'll have to do it over again because I don't remember it off the top of my head. So we have 25.0 milliliters of pyridine. Convert that to liters. 1,000 milliliters on the bottom, 1 liter on top. And then what are we going to do? Convert that into moles using molarity, liters, moles. So we have 0.21 moles per liter. It's equal to, and bear with me while I bang this calculation out real quick. I got 5.25. Yeah, okay, so it's 5.25 times 10 to the minus 3. I'm going to put this in just standard notation, 0.00525. How could I forget 0.00525? That is how many moles of pyridine that we that we have, right? Now, if we're talking about equivalence point, that means that we're going to need 0.00525 moles of HCl, right? So what's the volume here that we're adding, right? So 0.00525 moles, that's how many moles of acid we're going to need to react with all of our moles of pyridine here. That's going to be 0.10 moles HCl is HCl. And then that's 1 liter HCl. Then 1,000 milliliters, 1 liter. Okay. Units, liters. So it's going to be what volume? So again, I'm basically just calculating the volume that's required to reach the equivalence point here. 0.0055 divided by 0.1 times 1,000. That's 52.5 milliliters. 52.5 milliliters of HCl that we're going to be adding. That's the volume that's required to reach the equivalence. So, yeah. Let's sort of take that volume here and just sort of leave it, I don't know, here. I'll just highlight it with a, I'm going to get fancy here. I'm going to highlight it with this blue color here. Ooh. Never done that before. I usually just use the yellow highlighter. Anyway. All right. So we have the volume required to reach equivalence. We have the initial moles of pyridine. So really, I don't need any of this conversion stuff any longer. I really just need the room for my stoichiometry calculation. So I'm going to delete that. All right. So like I said before, very, very important that you can be able to write out the neutralization equation, write out what's actually happening, right? So what's happening, right? So we have H plus that's being added to our base, pyridine. That's going to produce the conjugate acid of pyridine. I'll just call it PyH plus, and water. Very, very important to be able to start with that. Otherwise, it's kind of hard to, have a chance of problem, right? So that's our equation. I'm going to take it and drag it just a little bit further over there. Okay. And so we're going to look at the conditions before. We're going to look at the addition. And we're going to look at the conditions after. Right? So we have approximately 0 moles of HCl, or H plus. Initially, we had the 0.00525 moles of pyridine, right? We have no conjugate acid just yet. What is the addition? Well, the equivalence point, right? So the addition is going to be the same as what we have here, right? So 0.00525 moles of H plus are going to be added to essentially neutralize all of our pyridine. So in other words, all of our pyridine here is being converted to the conjugate acid of pyridine by the reaction of this H plus that we added, right? H plus is converting a stoichiometric amount, 0.00525 moles of this pyridine into the conjugate acid pyridine, right? And so all of it is used up. We don't have any more, right? So we essentially have 0 moles of pyridine and 0.00525 moles of the conjugate acid of our pyridine, right? So now we have an aqueous solution in which it's not a buffer, right? Because in order for it to be considered a buffer, it has to have significant amounts of the acid and the conjugate base, right? Or in this case, the base and the conjugate acid. All we have here is the conjugate acid of pyridine acting as an acid in water, right? So it's like a standard equilibrium problem calculation at this point. So, but it's important that we can calculate the, that we can calculate the concentration of this PYH plus by remembering that we need to divide the amount in moles that we have by the total volume. And again, that's the volume that we had initially in our sample plus the volume of the acid that we add to it. Okay? So what is that? So it's 0.00525 moles, right? And then we're going to divide that by the total volume. So we have 25 milliliters plus 52.5 milliliters. So what is that? 77.5 milliliters? 77.5 milliliters, that's what? 0.0775 liters? I think that's correct. Is everybody following along with me? I really hope you are, and I really would hope that if you aren't, that you would let me know. So I'm not just talking to nobody. Oh. All right. So what is this value here? 0.00525 divided by 0.0775. That is the question. I will figure the answer to it out right now. 0.00525 divided by 0.0775. That is 0.068. 0.068. So we have the concentration of the conjugate acid of pyridine here, right? So now what I'm going to do is erase all this because we've gotten what we want out of this. Now we're going to do an equilibrium problem, right? So we have to be able to know how to write the chemical equations correctly for these equilibrium problems. And the best way to do that is to just think about what's actually happening. Like, okay, you know, we have the conjugate acid of pyridine, PYH plus, okay, that's going to act as an acid. That's going to donate a proton to water. And what do we get after it donates a proton to water? Let's write it down. So again, we have our acid, right, PYH plus. It's going to react with water. Since this is an acid, again, it's going to donate a proton because that's what acids do. They donate protons, right? They like to give up their protons to water, right? The water is going to say, hey, thanks for that proton. I'm going to act as a base and accept that proton. And so on the product side of the equation, what do we end up with? Well, we end up with just plain old pyridine, right? Because pyridine has lost, or the PYH plus has lost its H plus. And then we're going to end up with, what do you get when a water molecule accepts a proton? Well, you get H3O plus, the hydronium ion, right? So it's very, very important to be able to understand how to reason your way through that and write these equations out. If you know what's happening and you can sort of like imagine what's happening with the donating a proton and accepting one and all that stuff, then you won't have to memorize as much and you'll be able to just kind of like reason your way through the problem. That's how I recommend studying. But hell, what do I know? All right, so we're going to make an ice table, right? Initial change, equilibrium. Initially, we just established that we have 0.068 molar conjugate acid of pyridine, PYH plus, and we have essentially 0 of these two. The change is going to be minus X for the acid. It's going to be plus X for the products, right? And so at equilibrium, what do we have? Well, we have 0.068 minus X. That's the concentration of PYH plus. And then for pyridine and hydronium ion, they're both going to be X, right? Now, I did another foolish thing a few minutes ago. I had the Ka for the conjugate acid of pyridine. I had it, I calculated it, I stepped through the calculation, but I deleted it like a dumbass. So I'm going to have to calculate this again. I think we're ready to, I think I can delete all of this stuff to give myself some more room here. Bear with me for just a moment, guys. By the way, thank you all for being here. If you're new to the channel, I do these streams weekly on Sunday nights at 9 o'clock p.m. Eastern time, although last week I had to cancel mine because I had some dad duties that were calling at me. So yeah, so I do these streams weekly. We talk about chemistry, and I really, really would like to have your feedback and your participation, and I think that'd be cool. I like when things are more interactive. All right, so we need to get the Ka for the conjugate acid of pyridine, right? Now, like I said, I did this a few minutes ago, and like a complete dumbass, I deleted it. Now I don't remember what it is. So I'll just sort of talk you through it. Basically, you know, we understand that the product of Ka and Kb is Kw. I guess I could write that part out. So Ka times Kb is equal to Kw, right? Kw is 1.0 times 10 to the minus 14 at 25 degrees Celsius, called the ion product constant for water. So all you need to do to get your Ka is to take Kw and divide it by your Kb. So let me see if I can figure that out. You know, what I like about this calculator is I can scroll upward and like look at previous entries that I've made. So I actually just located the entry where I calculated this Kw value. So I can actually do this pretty easily. This is not as much of a pain in the ass as I thought it would be. Thanks to my calculator. Love this calculator. TI30X2S. Ah, it's great. All right. So Ka, let's see. Trying to figure out where I can move this stuff. So how about we take a nice table. I'll move it, let's say, down here. Okay, now I'm going to grab my purple pen and I'm going to Ka of Py H plus. And again, I'm calculating this by dividing Kw by our given Kb, right? So it's 5.9 times 10 to the minus 6. Demin just answered it for me too. Thank you, man. Thanks for being on top of this stuff, keeping me in check. Appreciate it. All right, so we have our Ka value, right? We have our equilibrium concentrations of everything in terms of X for this equilibrium reaction, right? So we know that the equilibrium constant, Ka, let's see, I'll do this in black. Ka is equal to, again, products over reactants, just as any equilibrium constants, right? So it's concentration of pyridine, concentration of H3O plus, those two multiply together, divided by the reactants, Py. No water, because we don't include water in equilibrium constant expressions. Okay, so that's Ka. So now we can just sort of substitute our values in terms of X in where they belong. So pyridine, what's that at equilibrium? Well, that's X, right? So I'll just replace that with X. H3O plus at equilibrium, it's also X, right? So really, X is what we're trying to solve for here, because X is the hydronium concentration, and it's the negative log of the hydronium concentration that is the formula for pH, right? So we're trying to solve for X here, or that's what we're trying to do. So we have X times X. Now I'm just going to rewrite that. Whoops. Get my eraser here. I'm just going to rewrite this as X squared, right? Times X. And then the PYH plus, what is that at equilibrium? Well, that's 0.068 minus X. 0.068 minus X, right? And that's equal to Ka, which we just calculated, which is equal to 5.9 times 10 to the minus 6. 5.9 times 10 to the minus 6. I'm wondering if there's a way I can drag this, keep it away from everything else. That's not it. Okay. There we go. Just keep it a little bit further away from everything else so it's not as cluttered. Okay, so we have this equation. This is a quadratic equation, and basically one of two ways we can solve this. We can either write it in the form ax squared plus by equals, or plus c equals 0, and then use the quadratic formula, which is a royal pain in the ass, or we can use the x is small approximation. So we're going to assume that the x is much, much smaller than the number that we are subtracting it from, in this case, 0.068, right? So we're going to just ignore it from the calculation because we think it's really, really small. Let's see. My eraser's not working. Okay, I accidentally opened up another program here. Bear with me for just a second. Okay, let's see. Okay, I think I got it working again. All right. So x squared over 0.068 is equal to 5.9 times 10 to the minus 6. So really, it's just some algebra, to clean this up and solve for x, right? And so we get, let's write it in, x squared is equal to the product of 5.9 times 10 to the minus 6 times 0.068. So to get from this equation up here to this equation down here, all I've done is just multiply both sides of the equation by 0.068 because we're trying to isolate this x, right? Okay, so x squared is equal to this product. Now, if I want to solve for x, that's pretty simple. I'm just going to take the square root of this product, right? So x, which, by the way, is equal to the H3O plus concentration at equilibrium, right, is equal to the square root of the product of 5.9 times 10 to the minus 6 and 0.068. So, allow me to calculate that. I need to play like the Jeopardy music. That'd be funny. Okay. Square root. Okay, what did I get? I got... Wasn't trying to use the highlighter there. My bad. I got x is equal to... And again, this is really the H3O plus concentration is equal to... I got 6.33... Let me try that again with better handwriting. 6.33 times 10 to the minus 4. 6.33 times 10 to the minus 4, right? And so finally, to calculate pH, all we need to do is to take the negative logarithm of this, right? So let me clean this up a little bit. I don't need this anymore. We're done with that. Okay. All right. So easy peasy. All we have to do is just say that pH is equal to negative log of the hydronium concentration. So negative log of 6.33 times 10 to the minus 4. And that is equal to, I don't know yet, because I haven't put it in my calculator yet. Join me. Negative log. And I got a value of 3.20. That's if you round it to 2 decimal places, but that's it. 3.20. That is our pH, the equivalence point, right? And again, this is a weak base, strong acid titration. So this isn't something that I've seen before or that I've talked about before. Like I've just been doing like titrations that involve titrating an acid with a base. This is titrating a base with an acid, so it's a little bit different, but it's essentially the same principle that applies as the acid is added, the strong acid is added, it converts a stoichiometric amount of that base into its conjugate acid. And before you reach the equivalence point, it's a buffer, right? So the solution becomes a buffer as soon as you start adding the HCl to it, right? Because you have weak acid and conjugate base in there. But then once you reach the equivalence point, you no longer have a buffer. You just have a weak base, or a weak acid solution at that, because it's the conjugate base or conjugate acid of a weak base. So, all right, guys. So we did equivalence point. We did what? I can't remember the other ones that we did. We did 0. I definitely remember doing 0 milliliters and 10 milliliters. But it is 11 o'clock now. I've been going for 2 hours, so unfortunately, I should get going. Maybe I'll come back on at some point and do these again. But yeah, I think I'm going to call it a night, guys. This is, I think, the longest stream I've ever done. I should have known it would be this long just because titration problems take forever. But I hope, even though I didn't complete all of what I had prepared, I hope that it was still of some value to you. And I would hope that either way that I would get some feedback, whether it's valuable or not. I tried a lot of things out tonight that I haven't done before the first time. So again, I hope it was helpful. If you want to see more examples like this in the future, or if you want to see like anything at all, like just let me know what you do want to see. And I do want to, I want to be able to provide what the audience wants. So enough people tell me the same thing, and I'll be compelled to make a video on it. So, all right. Thanks again, everybody. I'm going to end the stream, and I will talk to you guys later. I stream Sunday nights, 9 o'clock Eastern, 9 o'clock p.m. Eastern on Sunday nights. And all right. Take care, everybody.